on Gotham's Reckoning. Here to end the ball of time you all been living on.
All right, you guys got me. I am an opportunist. There's no way, no possible way I'm putting this thing on and not trying to imitate Bane. No possible way. It's just in my nature, I have to do it. So hope you enjoyed that. You might see it again, maybe. Anyway, so this is a training mask used for specifically hypoxic training, or at least simulating hypoxia. So I'll get into this later on, not in the PowerPoint itself, but towards the end of the lecture. Also comes with different little attachments here that you can put in to these little spots here where you actually breathe air in and out. And they have different resistance to them. We'll get into that later. And also something that I did mention and that I will mention, I've already recorded it, but something that I will mention here in a little bit is a pulse oximeter. So this chapter was looking at altitude and the science behind it. Why is it tougher to exercise and to really even just at rest breathe? Why do you have a harder time at altitude? And go into the specific reasons why that is. So we refer to it as hypoxia, and that hypoxia is really specifically looking at the partial pressures of those specific gases. Namely, oxygen is the most important one there. And I'll go into some of the specifics about it, some of the science and reasoning of why we have a harder time. So I hope you enjoy the chapter, and I will see you after I am done speaking about hypoxia. Physiology and training at altitude. And what we're discussing here is the concept of hypoxia. We will get into the reason why we have a picture of Patrick Swayze up in this slide here in 1 second. So to look at the concept of hypoxia, we first need to look at the pulmonary diffusion of gases. So I'll try to break this down in somewhat of a simplistic form here. So when we look at the gases in a mixture, say if you take a balloon of just regular air, each one of those gases in the mixture has a pressure. And if you split that up, that's the partial pressure of each one of those gases. And each one of those gases' partial pressures should equal the total amount of pressure. This is known as Dalton's law. So the total pressure is equal to the sum of all of the pressures of the gases within a mixture. And that's the reason why I have Patrick Swayze there, because his name was Dalton in the movie Roadhouse. Roadhouse. So let's look at the idea of partial pressure from a mathematical standpoint. If we take the average air that we breathe in, again, no pollution, no strange environment that we are in, the average makeup of that air is consisting of approximately 79% nitrogen. So nitrogen is actually most of the gas that we are breathing in. And then oxygen is approximately 21%. And then we have carbon dioxide, which is bringing up the rear at 0.03%. So well below 1%. Again, this is a typical amount in percentage within the air that we breathe. The pressure at sea level is 760 millimeters of mercury. So that's the barometric pressure at sea level. So if we look at sea level itself and take that 760 millimeters of mercury, and if we multiply it by 0.7904, we will get 600.7 millimeters of mercury. So that's the partial pressure of nitrogen at sea level, so long as the pressure, the barometric pressure, is 760 millimeters of mercury, and that air is 79% approximately nitrogen. Now, if we take that same 760 millimeters of mercury and multiply it by approximately 21% or 0.2093, we will get 159 millimeters of mercury. That is the partial pressure, or the PO2, of oxygen at sea level. If we take that same 760 millimeters of mercury and multiply it by 0.03% or 0.0003, we are then going to be getting 0.02 millimeters of mercury, and that is the partial pressure of carbon dioxide at sea level. So even though some of these numbers are rounded, if you add up these numbers, you will get approximately 760 millimeters of mercury. So each one of those gases has a pressure, and each one of them is known as a partial pressure to the total pressure. So adding all of those up, that is going to be the sum of the partial pressures, thus equaling the total pressure. Now, for gas exchange to occur within the lungs, and this is going to be the important part of why we may have some difficulty at altitude or a low oxygen environment, is that the pressure gradient is the major factor in gas exchange at the lungs. So let's dive deep into the lungs. So this little group of sacs here almost looks like a little thing of grapes. This is actually known as the alveoli. So these alveoli, this is where we're going to have the gas exchange. And this is a cross section of this alveoli. And these little red spots here, those are the capillaries. And then blowing that up, we have a membrane then, where over here we have the capillary membrane and we have the alveolar membrane on the other side. In this space here, where these two membranes meet, that's known as the respiratory membrane. This is where the gas exchange occurs. Oxygen will be transported across this membrane, thus allowing us to bring oxygen into the blood, carbon dioxide out of the blood, so that we can exhale the carbon dioxide then and get rid of that waste. All right, so what do we mean by altitude? We're really just looking at the atmospheric pressure, or that ATM. So how many atmospheres are we at? So at sea level, we're at 1 atmosphere. As we go up, we get less and less atmospheric pressure, lower than 1 atmosphere. Now, as we climb in altitude, we have the same percentage of those gases, oxygen, carbon dioxide, and nitrogen. However, since the total pressure has now decreased, we have a decrease in the partial pressures of those gases. Think back to when we looked at hyperbaria and Boyle's law. So pressure is inversely proportional to volume. So if you take a balloon at sea level, blow it up to a certain diameter, and then take it up to altitude, that balloon will increase in volume because the pressure has now decreased. So some terminology to look at: hypoxia is just the low partial pressure of oxygen. Normoxia is what we experience at sea level. And then hyperoxia is that high partial pressure of oxygen, such as going below sea level. So let's look at this chart. Let me blow it up here a little bit so we can see it a little bit better. So we have a few different places that are represented on this figure. We have Miami, which is at sea level, Denver, Mexico City, Pikes Peak in Colorado, and then we have Mount Everest. And we can see the corresponding altitudes in feet as well as in meters at each one of these locations. And we can look at the barometric pressure at each one of these locations. And as you can see, as we go up in altitude, the barometric pressure is going to decrease. But the percentage of oxygen within the air is remaining exactly the same no matter where we are at. So if we take that 21%, multiply it by 760 millimeters of mercury, like we did in a couple slides ago, that partial pressure is now 159 millimeters of mercury. So the normal partial pressure of oxygen that we experience, at least at sea level. And in Ohio, we can assume we are close enough to sea level where this isn't going to change all that much. Now at Denver, we have 631 millimeters of mercury multiplied by 21%, gives us approximately 132 millimeters of mercury, and that's the partial pressure of oxygen at Denver then. If we go somewhere like Pikes Peak in Colorado, at 430 multiplied by 21%, we are now down to 90 millimeters of mercury. So this is going to have drastic effects on how our bodies are going to be responding to that atmosphere. And the same thing at Everest. You'll hear stories and you can watch documentaries and you watch a lot of videos on climbing Mount Everest and what they have to do to get there, possibly breathing in additional oxygen. So again, it is not the percentage of oxygen within the air, it is the partial pressure of the oxygen within the air. So another way to describe this is that if you breathe in a certain amount of air, let's just say a half a liter at sea level versus a half a liter at Pikes Peak, that air is made up by the same percentage of oxygen. However, the molecules, the oxygen molecules, have spread out further in the total air, so you are bringing in less oxygen for each breath. So the volume has now increased so much due to the lack of pressure that the molecules are spread out and you are breathing in less and less molecules, oxygen molecules, for each breath. So let's see how this can play a role in physiology. Now this might look somewhat confusing, but let me try to break this down for you in simplistic terms. Basically, we're going to have a tough time when we go to altitude. On the left here, we have a normal situation, say at sea level. So the partial pressure of oxygen is 159 millimeters of mercury, and that is within the alveoli. Now, once we get into the arteries going into systemic circulation or back to the heart and going into the muscles, we end up with approximately 100 millimeters of mercury of oxygen partial pressure. Now, the reason it decreases as we are coming back to the heart and going back to the lungs is because we have more carbon dioxide and we have less oxygen. Now, if we look on the right, we are starting off with a lower partial pressure of oxygen. Thus, once we get down into the lungs, as well as the systemic circulation or circulation going back to the heart from the lungs and then to the muscles, we are now at approximately 42 millimeters of mercury, much lower partial pressure. This has drastic consequences on how we are getting oxygen to the muscles and to all the tissues that we need it to get to, so that we can actually go through metabolism and contract the muscles. And our bodies are going to try to counteract this, and we'll get into some of that. The cardiorespiratory capacity during hypoxic situations. So there's going to be an increase in respiration, and this is going to be due to chemoreceptors or receptors in the body that are going to be responding to low oxygen levels and also high carbon dioxide levels as well. So there's a reduced work due to the low air pressure. However, even though there's a reduced work, you're going to be working a little bit harder even at rest, even up to approximately 10% of VO2 or volume of oxygen that is consumed, and your breathing rate is going to be increasing at rest. So there's going to be an increase in heart rate as well as a decrease in stroke volume because your heart rate is increasing so much that you're not going to be able to pump enough into one side of the heart to allow the heart to fill up nearly as much. The increase in heart rate and respiration are the two biggest responses to hypoxia. Now, when we look at the oxygen requirements, there is no difference between the required oxygen for a certain exercise intensity at sea level versus hypoxia, at least up to approximately 25,000 feet. And this oxygen requirement is referring to the consumption that we need in the utilization. Now, when we look at maximal level oxygen consumption and utilization, this is going to be decreased with altitude. Going into some specific numbers, you obviously don't need to know this. There's no exams or anything, but just to give you an idea, we go from 1.5 liters per minute versus 4 to 6 liters per minute. And that's a difference between 24,000 feet and sea level. So we're decreasing quite a bit in terms of the maximal amount that we can consume from 4 to 6 down to approximately 1.5. That's a drastic decrease. At approximately 15,000 feet, or roughly Pikes Peak in Colorado, the decrease in the maximal amount of oxygen that you can utilize is about 26%. Now, all of this is based upon, and the reason why we decrease the maximal oxygen utilization is because the arterial saturation, the amount of oxygen within the arteries, going back to this chart, this is the reason why the arteries have less oxygen, is because we're starting off with lower partial pressure. Thus, we're starting off with lower oxygen within the blood. So that arterial saturation is really the key factor here. Under normal circumstances, your arterial saturation is approximately 96, 97. In fact, there's a small device that you can use to measure this. It's known as a pulse oximeter or a pulse ox. They're readily available. You can buy them on Amazon. You might get them at a doctor's office. Sometimes they'll put them on your finger before you're going into surgery. Under a hypoxic situation, you may have an arterial saturation of in the mid 70s. So maybe like 74, 76, somewhere around there. Two charts just showing the heart rate and ventilation or the breathing patterns of humans when they're going into a hypoxia situation. So the heart rate on the y-axis and then oxygen consumption, basically looking at the increase in intensity of an activity, is increasing obviously even at sea level, but at 10,000 feet, we're even starting off at a higher heart rate. And that heart rate is increased over given exercise intensities. Now, the ventilation on this side, we have ventilation. This is in liters per minute. And then oxygen consumption, again, intensity increases. At each elevation increase, we are increasing the pulmonary ventilation even at rest or at a low oxygen consumption, and then increasing it even more so as we continue to increase the intensity. Like I was saying before, there is a decrease in the VO2 or the maximal oxygen consumption at altitude versus sea level or lower altitudes. And the major factor here is the oxygen extraction, as well as the decrease in the arterial saturation, sometimes referred to as SaO2. Now, if we look at the figure here, and I'll blow this one up, you can see it a little bit better. Oh, well, there we go. That looks nice. So as we increase in the altitude in meters, in this case, we have Mexico City, we have Leadville, Colorado, and Nunua, Peru, I believe is how you pronounce it. We are continuously decreasing the maximal amount of oxygen that we can consume. And this is actually based upon a percentage of that maximal oxygen consumption. So you can see here, the one in Peru, we have decreased approximately almost 30% of our maximal oxygen consumption that we can get to. That means that your max exercise is going to be lower. You cannot work as hard as you can at sea level versus any of these locations. Now, getting into some of the responses of the body other than the increase in heart rate and ventilation, we have what's known as polycythemia, and this is an increase in the red blood cell production. Red blood cells are very important for oxygen carrying capacity. So within the first few days of exposure, there's actually an increase in what's known as hematocrit, or HCT, and this is simply showing an increase in the amount of red blood cells. There's also a slight decrease in the plasma, which helps to increase that hematocrit, because hematocrit is essentially a percentage concentration of red blood cells versus the total amount of blood. Now, this can affect performance because that decrease in plasma is showing that there is a slight dehydration, and with thicker blood, this can cause some somewhat sludginess and slowness of the blood to get around. However, this will take effect to the point where you're going to increase the plasma volume and maybe not get up to sea level levels with the amount of oxygen carrying capacity in terms of actually efficiency, because again, we still have low partial pressure of oxygen. However, this will lead to a counteraction to increase the ability to work out at high altitudes. Again, maybe not to the sea level capacities, but still better than the first few days of exposure. The main reason why the increase in red blood cell production happens is because a hormone known as erythropoietin, or sometimes referred to as EPO, is increased and released in the body. Now, this is a little bit different than the EPO that you may have heard of with blood doping. Blood doping has a couple of different versions of it, but the EPO version, that's more of a synthetic version of the EPO. The natural version of red blood cell production is erythropoietin. And you can do it naturally by going to altitude. And we'll see some ways to actually do this correctly, or at least somewhat correctly, based upon the research. All right, looking at some details of metabolism. So the aerobic metabolism, there is a lack of oxygen, but there is an increased reliance on the anaerobic metabolism, because with anaerobic metabolism, you're not using oxygen, obviously. So there's less ATP per gram of whatever the anaerobic metabolism is using, normally carbohydrates, for energy production. Again, that ATP is going to be that energy molecule that we use. Now we're going to become more fatigued and much quicker because of the lactate that is being produced. And it's just not the lactate. There's some hydrogen there that is associated with the lactic acid production that causes a decrease in the pH of the blood. And that's what's actually causing the fatigue then with the anaerobic metabolism. So what can happen when somebody is exposed to high altitude in terms of becoming sick or some really negative effects other than performance? So we have this acute mountain sickness that can develop. This is normally seen at greater than 2,500 meters within about 6 to 12 hours of initial exposure. The symptoms of it include headache, fatigue, irritability, nausea, could be vomiting, maybe loss of appetite, flatulence or farting, if you want to put it that way, constipation, as well as any type of sleep disturbances. Now, someone can experience one or multiple of these, or possibly even all of them, depending upon how somebody reacts. Some people will get acute mountain sickness, some will not. It just depends upon the individual. The reason this occurs is because there's an increase in cranial pressure and possibly even some lung swelling that's occurring because of the fluid redistribution within the body. Because we're losing some water, we're gaining maybe a little bit more of the red blood cell production. Our bodies are kind of in a protective mode because they don't know exactly what's going on, but they're counteracting it the way it knows best to do. So we have an impairment in oxygen as well as carbon dioxide exchange. Now, if this continues and progresses into something a little bit worse, this is going to be referred to as high altitude cerebral edema, or HACE. So this is a progression, again, of the acute mountain sickness. There's a further increase in cranial pressure, in spinal fluids as well as the pressure. There's also some cerebral blood flow increases and changes to the blood itself. That blood-brain barrier, there's going to be a little bit more permeability. So we have an increase in fluid development. This can cause some incoordination of the muscles and sometimes referred to as ataxia. If it gets severe enough, it can cause headaches to the point where they almost feel like migraines or really, really heavy headaches, something that is extremely painful. And then the last one, known as high altitude pulmonary edema, or HAPE. This is a lot of times seen in young, healthy, and active individuals, and it can be fatal if untreated. This is, again, a more of a progressive type of acute mountain sickness. So this is going to be fluid buildup within the lung, or the thoracic cavity in this case, versus the cerebral cavity. The best way to prevent either HAPE or HACE is to ascend slowly to the altitude. Let's get into some of the concepts of how we can use this physiological response to altitude to our advantage. So athletes always want to gain an advantage, and there's an intermittent hypoxic training that has been developed. It can either be natural or man-made, and on the right here, you can see these tanks. I actually used these for my dissertation, and over here was actually a chamber, and I'll show you a picture here later on of the full chamber. But these tanks were to scrub out or remove oxygen from a room so that it was lower oxygen. Now, it wasn't hypobaric hypoxia, but we lowered the percentage of oxygen within that room. Same concept applies as we were at altitude, but we were actually right about sea level. We were just decreasing the percentage of oxygen. Now, there's really not necessarily an ergogenic effect to this, meaning that helping you to work harder. There could be some hematological parameters, so changes within the blood, plasma volume, hematocrit, red blood cell production, potentially, depending upon how you use it. You could have some changes in VO2, but we need to get into some of the specifics of living low, training high. So what does it mean to live low and train high? It just simply means living at a low altitude, possibly sea level, and then training at a high altitude. So the limitations to this are, there's been a lot of lab trials with a man-made type of device. So the motivation isn't necessarily there. It's not necessarily practical, simply because the equipment is really expensive. The equipment that I used in my dissertation was tens of thousands, if not a little over $100,000 for the entire thing that we had, the room and all of the other ancillary equipment that went along with it. It lacks specificity, and that specificity is referring to the actual environment. That environment that my subjects were in was a normobaric hypoxia. So actually going to altitude, experiencing the weather, experiencing the hypobaria, experiencing running up and down hills at hypoxia, that's going to be more specific to someone's training than being in a very controlled setting. So not performing any time trials in the actual environment can be a hindrance on performance increases, if any would be seen anyway. So are there some possible benefits? Yeah, low landers, training for competition at altitude, certain military branches, and also trying to diminish initial limitations of altitude exposure. Getting somebody used to the altitude, what's going to happen when they are exposed to maybe low oxygen environments or low partial pressure oxygen environments. And the next concept would be living high and training high. So this is living at altitude and also training at altitude. So some of the non-physiological factors related to this, you might have access to better equipment, better training, coaches. There's maybe some camaraderie that's involved with this because everyone could be training at this altitude. You're going to be living with other individuals at this altitude, but the physiological effects might not necessarily be the best. The VO2 max is not increased after returning to sea level, even though there might be some adaptation that occurred at the altitude and they were still training during that period of time. It did not translate into an increase in VO2 max at sea level. So any type of time trials have not seemed to be significantly different, such as the time it takes to run a specific race. Let's look at one study that was performed on this, living high and training at high altitude. And this was with US distance runners. So they had 2 periods of 14 days at 7,500 feet. The VO2 max increased after both trials. The performance times improved and the personal records were set by most of the runners. However, there was really no true control group. There was no other group to compare them to see if it was the altitude or if it was the type of training that they were performing at that altitude. But most of the research shows that living high, training high isn't the most beneficial. Now let's look at the concept of living high and training low. So living at a high altitude, training at a low altitude. Right off the bat, I'll tell you that this tends to be the most preferred method of utilizing the responses and the adaptations to high altitude. So you're maximizing the adaptations or the adaptions while maintaining high intensity exercise. So that living at high altitude means that you have 8 to 10 hours of rest or sleep. So you're basically sleeping at altitude. Then during the day for the training, you are coming down to a lower level, to near possible sea level. So you're training lower. The reason this tends to work is because living at that altitude, even 8 to 10 hours of just sleep and rest at altitude, the body will develop the adaptations to the high altitude. Red blood cell production, better heart rate response, better breathing responses. But at the low altitude, you can maximize the intensity. There is no decrease of the VO2 once you go down to sea level, like you would if you maintain that high altitude exposure. So you can maximize those adaptations or becoming adapted to the low partial pressure of oxygen, but at the same time, you have this high intensity exercise that you can perform. So if you look at it, it is legal in natural blood doping. You're increasing the red blood cell production by hormone known as EPO or erythropoietin, and you're able to increase the intensity of the exercise during the training. Now let's look at one study that actually studied this a little bit. So they took some collegiate runners. So they lived at a high altitude, 8,200 feet, and trained at a low altitude, approximately 4,100 feet. In this case, there was a control group, one that was living and also training at low altitude. And then the experimental group was at high altitude, living and training at the low altitude. So there were some high correlations amongst all the individuals. There was an increase in hemoglobin, which would be the red blood cells, increase in VO2, and also increase in performance, such as time trials. And this was in the experimental group. Now, there was no change in the control group, however. But one problem with this study is that some of the studies couldn't replicate the results to this. Some of that could be the individuality between the individuals, could be the type of training that they had during the actual training process. The other reason that it could have not been replicated is this was 8,200 feet versus 4,100 feet, although that is a fairly significant difference in altitude. More than likely, there would have been a better response if those two numbers were further apart, say 10,000, 12,000, maybe 14,000 feet, and say sea level. Now, how does this affect performance? When we look at peak power output, especially of short duration exercises and races, there's actually not a decrease in the performance. Now, if it's a repeated sprint or repeated short burst of activity, then yes, there was a decrease in performance. However, if it was only one bout, so if we look at 100 meters, there was a decrease in the time that it took for that person to run between 1964 and 1968, Tokyo being at sea level and Mexico City being at altitude. Now, a tenth of a second doesn't sound like a lot, but in 100 meters, it's quite a bit. If we go to something like the 400 meter run, it was almost a second and a half in the 400. That's quite a bit. Now, why does this happen? Well, the reason is because those events don't rely heavily on oxygen. It's anaerobic, and there's actually a decrease in the wind resistance at altitude. It's the same reason why baseballs can fly higher. The air, quote unquote, is thinner. Baseballs can fly further, and in fact, at Coors Field in Colorado, they have started to put their baseballs in humidors, which are normally reserved for cigars, so that there's a little bit of moisture in the leather of the balls so that they don't fly nearly as far. Now, in long distance events, yes, there is going to be a significant difference in what somebody can do in the performance of the time trials. But in short duration anaerobic exercises and events, there could actually be a performance boost because of the thinner, quote unquote, thinner air. Applying the altitude training. So we have this loss of acclimatization, and this is going to be individual. So we have this loss of acclimatization, those adaptations that develop normally over a 3 to 4 week period. And without that exposure, they're going to be gone usually within a couple weeks. But any type of tents, chambers, anything that is helping to decrease the oxygen content that's getting into the body, that's going to help maintain at least some of those adaptations. But actually going to altitude or sleeping at altitude, that's what's really going to maintain those adaptations. Looking specifically at the sea level to altitude transition, just using a tent or some other device isn't specific to other training methods, because if you're not actually performing those events inside of those chambers or with that piece of equipment, then it's not specific to what you're going to be doing during that activity. So there's a specificity that needs to be applied to this competition altitude training. So about a day and a half, 2 or 3 days prior to the competition, there is still going to be an improved heart rate and exercise tolerance versus maybe just 6 hours prior to the competition. So allowing for some sort of at least acute adaptation to occur, but again, allowing long-term adaptations to occur. And that's going to take approximately 2 to 3 weeks, roughly, depending upon the individual. So to sum this up, the acclimatization is the increase in the gas exchange or the efficiency that is occurring when exposed to those low oxygen environments or the low partial pressure of the oxygen. With that response, the EPO hormone is released, the erythropoietin, that increases red blood cell production, hemoglobin, which is part of the red blood cell production. It's the goop inside of the blood, but also something else is increased, and that's the myoglobin. Myoglobin is just like hemoglobin, except that it is inside of the muscles. That's the oxygen carrying cell within the muscles. So I want to show some pictures that I took when I was in grad school, and this was the actual device that I used for my dissertation. So we've seen this picture earlier. These were known as scrubbers, and their sole job was to bring out the oxygen in the room. And the room was this room over here. It was aluminum framing, but it was this kind of clear, rubbery material. It wasn't glass or anything like that. And it made a nice seal with the floor as well. So it was fairly airtight, except when you open the door. This computer controlled the environment. And this device right here, you could actually increase. And that was determining how much oxygen you were pulling out of the room and what the simulated altitude was. So I was actually simulating Pikes Peak, so roughly 14,500 feet. And this is where the air was actually coming out of the room and then into these little scrubbers here. So they were scrubbing the air. And this is a wider view of it. So this was the entire room. There was one bike in there. And the reason I wanted to show you, it's not to brag or anything, which, I mean, I think it was kind of cool to be able to work with pieces of equipment like this, but just to show you that you don't necessarily have to go to altitude to be able to test these things. We can simulate the altitude with devices like this. Now, there are cheaper versions of this. There are other companies that make something similar to this that do the same thing, but somebody could invest in something like this, maybe a little bit smaller, put a small bed or cot in there, live at quote unquote altitude or simulated altitude, and then work out, go right outside of the room and work out in a normal oxygen environment. So they would be living high, living at a high altitude, and training at a low altitude. So that was physiology and training at altitude, or hypoxia, as we call in the biz. And you're going to see my good friend here in 1 second.
You think darkness is your ally. You merely adopted the dark. I was born in it, molded by it.
Okay, I do have actually a little bit of a confession to make. That wasn't actually me speaking through this thing while I was trying to do the Bane impression, because it's actually pretty difficult to breathe through this device. And I'll demonstrate it here in a second. And I'll demonstrate it here right now. You probably didn't hear me. So I'm putting it on right now. Okay, I think you can kind of hear me a little bit. So you can hear me, but it's still a little bit difficult. I think you can kind of hear me just a little bit coming through the microphone, but it is somewhat difficult to breathe. There's a lot of resistance. So let me get my stuff back on and I'll come back to you here in 1 second. Okay, so this little thing right here, this awesome Bane mask, Bane altitude mask is what I'm going to be calling it. It's interesting because the whole concept is there's resistance breathing in, meaning that you're not going to be able to get as much oxygen into your blood, which should work to create a hypoxic situation and decrease the arterial saturation. And will it help in certain circumstances and maybe even help to increase the adaptation and training for breathing and the respiratory muscles? Sure, it possibly could. But in terms of altitude, as we've seen towards the end there, that it's the living at altitude and being exposed to it for long periods of time. That's what's really going to help to increase the potential for adaptation to occur. And at sea level, training at high levels then. So that live high, train low. So for this to work in terms of adaptation to altitude, you would need to sleep with this thing on. I don't know if I would do that. There's different things that I mentioned at the beginning of the video. Let me get these out. So there's different devices here. I guess not really filters, but you can put these on, and you can see the one that is on it only has one little area here where the air can escape, and these other ones, that one has 2, then that one has 4 surrounding them. How are you doing? I gotta play it around. I'm a goofball. So these, you can put these in here, and these will simulate different altitudes depending upon which one that you want. Obviously, the one that has more of the holes, which is the 4, is going to simulate a lower altitude. The one that I have in right now is simulating somewhere around, I think, 12 or 14,000 feet, I believe. Now, again, it's something that could be beneficial, but at least it simulates at least a little bit of what altitude training could potentially be, especially if you're exercising at a fairly high intensity. The research, again, you can maybe have some type of training effect, but in terms of adaptation to altitude, probably not going to work with something like this. Again, I think it's a cool device. I think it's something that you can maybe use it somewhat, but I can't remember how much these were. But again, cool little devices. I think there's a place for them. You have to look up some of the research behind it. I'll be honest, I don't know if they really, looking at from the physiology standpoint, in adaptations with high altitude, you would have to sleep with this thing on for any type of significant adaptation to occur with this, at least from a hypoxia adaptation standpoint. So anyway, and with breathing training, respiratory muscles, things like that, you could actually have some adaptation that way. But for adaptation to hypoxia, having the EPO and the red blood cell increases, probably not the best option. There's other devices that could maybe work a little bit better, where you could sleep in a certain tent or room that is lower oxygen, that'll give you the benefit there. And it's still going to be easier to breathe than something like this. Okay, the other device I wanted to point out was this guy right here. This is the pulse oximeter. So this thing, or sometimes known as the pulse ox, this thing actually measures the oxygen content in the arterial blood, the arterial saturation, or the SaO2. It also takes heart rate. Oh my goodness, my heart rate is way up. I've been kind of moving around and everything. That's kind of that's dangerous. That's terrible. So my SaO2 right now is 97. I believe it was just 96 or so, just a little bit ago. So again, that's the average, 96, 97, somewhere around there. If it was a low oxygen environment, it would be somewhere probably in the mid 70s, or at least low 80s. It shouldn't go too low. It should be like 50%. That's way too low. That's a bad time. Okay. But again, it gives you the heart rate as well. So something simple as that. These are fairly cheap. You can find these just about anywhere. I think even drugstores and stuff like that will sell these as well, because it's actually beneficial for certain individuals. And during this period of time for COVID, I believe people who are quarantined are actually getting these to kind of monitor themselves as well. Oh, and by the way, this probably isn't the best thing. If you have one of these, I don't know if it would be very good for preventing any type of viruses or anything like that, like COVID, just because there's going to be, there's diaphragms in here that once you breathe out, it causes them to move, and then there's an open air. So the virus or anything is going to get inside of there. So probably not recommended for that, but still neat. If I think about going outside, going to Walmart or something like that with this thing on and just walking around and see what happens. I don't know. I'm weird like that. So I hope you liked the lecture. This was actually a combination of two different lectures kind of put into one, that I was going to go over hypoxia or high altitude, and then go over kind of some of the training and things like that. But I decided to just put them together all in one. It makes for maybe a little bit longer video, but Hope you enjoyed it. Hope you enjoyed my references to The Dark Knight Rises, but also Roadhouse. And I hope you enjoyed the pictures that I showed in the last couple lectures, referring to some of the equipment that I used in grad school. I wish we could have some of that stuff here, but it's really specialty equipment and it's really expensive. Yeah, but if you ever get a chance to use any type of equipment like that, uh, man, take the opportunity to do it because it's really interesting to see what happens. A story that I always like to tell is in my dissertation, I experienced it firsthand what happens as soon as you walk into that room. Again, we were simulating about 14,500 feet or so. And I would have to be in there with the subjects during data collection while they were exercising. So it was 2 hours of resting, and I was outside of the tent or the chamber, that little room. And then there was an hour of exercise, and then they had an hour of recovery. During the exercise portion, and about 15 minutes pre and post, I was in there with them. So I was in there for about an hour and a half with them. And as soon as I got in there, I mean, within 10 seconds, you can feel it. You can feel your heart rate rise and your breathing rate. You could feel it rise. And if you've ever been to altitude, you kind of know this, especially if you go to altitude really quickly, like getting off a plane or something like that, you're in a different elevation. And after about an hour, even just standing there, I mean, it was pretty intense. I mean, I could feel it quite a bit, even just standing there for about an hour or hour and a half. And I was happy to get outside of that chamber when we were doing the hypoxia data collection. So anyway, I hope you enjoyed everything about this chapter. If you have any questions, any comments, anything, again, I'm going to reference you to, and you can buy these on Amazon. These are kind of free to buy for anybody, as well as any pulse oximeters. You can buy hypoxic tents and chambers and everything. There's commercial ones, and there are ones that just kind of anybody can get. Of course, anybody can buy any of them as long as you have enough money. But again, some of those can be quite expensive. I think some of the cheaper versions of those tents, they can be in a few $1,000s or something like that, $4,000 or $5,000, just depending upon how big it may be. But literally, some of them are just tents. It's basically like a tent, and you have one of those little scrubbers that scrub out and pull out the oxygen so that you can sleep in this thing, or you can put a bike in it, or maybe a small treadmill or something like that where you can exercise in it. So you can look those up, and maybe I'll put a link of at least one of them down below. So if you have any questions, you have any comments, please let me know. And I thank you for watching.
And we give it back to you, the people.